Level 0. The sky flashes. You glance up, expecting to see a lightning bolt striking somewhere, but there's nothing. Just the cloud itself lighting up for a split second, like someone turned on a lamp inside it. No drama, no fork splitting the sky, just a soft pulse of light that fades back to gray. Seems harmless, right? Boring, even. But inside that cloud, 100 million volts, just ripped through miles of ice and vapor at temperatures that would vaporize steel in microseconds. Welcome to intra-cloud lightning, where the storm fights itself in silence, and 3 out of every 4 lightning strikes never even try to reach you. Before lightning ever reaches the ground or jumps between clouds, it starts inside a single thundercloud. This is intra-cloud lightning, the most common form of all lightning discharges. About 75% of all lightning never leaves the cloud where it originated. It's the storm arguing with itself. Inside a thunderstorm, violent updrafts and downdrafts cause ice particles and water droplets to collide constantly, creating regions of positive and negative charge separated by distance. When the electrical difference becomes too great, typically around 100 million volts, it discharges within the cloud itself, jumping between the positively charged top and negatively charged middle or bottom. The mechanism is fascinating. Small ice crystals, being lighter, get carried upward by the updraft to the top of the cloud, where they accumulate positive charge. Heavier graupel and hail pellets, loaded with negative charge, sink toward the cloud base. This vertical separation creates an enormous electric field, like a battery the size of a mountain. When the voltage difference exceeds the air's ability to insulate, the breakdown occurs in a fraction of a second. The channels that form inside the cloud are complex networks, not simple straight lines. High-speed photography reveals intricate branching patterns, with the main channel splitting into dozens of smaller tributaries. These branches can extend for miles inside the cloud, creating a three-dimensional web of ionized pathways. Some researchers compare it to lightning roots growing through the cloud's interior. From the ground, you see the entire cloud light up from within. It's like watching a lamp turn on inside frosted glass. The flash illuminates the cloud's internal structure for a split second, revealing towers and valleys of water vapor. Photographers and storm watchers call this sheet lightning because of how it spreads across the sky in broad, diffuse flashes. Each flash can release over 1 billion joules of energy. The channel inside the cloud superheats to 30,000 Kelvin, creating shock waves that rumble as thunder. But because the lightning is hidden inside the cloud, the thunder sounds muffled, like distant drums rather than sharp cracks. The cloud itself acts as a massive acoustic dampener, absorbing and scattering the sound waves. Temperature gradients inside the storm also affect how the thunder propagates. Sound waves travel faster through warmer air, causing them to refract and bend. This is why thunder from intra-cloud lightning often seems to come from multiple directions simultaneously, creating that characteristic rolling rumble that lasts several seconds. Scientists study intra-cloud lightning because it reveals the inner workings of storms. By tracking where flashes occur inside the cloud structure, meteorologists can predict when conditions might become severe. It's the storm warming up, building charge, preparing for something bigger. But what happens when one cloud's charge becomes so powerful it reaches across miles of empty sky to connect with another storm? Level 1. Once a storm has built up enough charge inside itself, it starts looking for new places to discharge. Enter cloud-to-cloud lightning, where electrical bolts jump between separate thunderclouds. This is the storm expanding its reach, connecting with other electrically charged systems miles away. Cloud-to-cloud lightning occurs when nearby storms or different cells within a storm system develop opposite charges. The lightning channel bridges the gap between clouds, creating spectacular horizontal bolts that can stretch for miles across the sky. Unlike intra-cloud lightning that stays hidden, these discharges are often partially visible, appearing as bright channels connecting cloud masses. The formation requires precise conditions. Two storm cells need to develop opposite polarities, with one accumulating predominantly positive charge while its neighbor becomes negatively charged. As these electrical potentials grow, the air between them becomes increasingly stressed. Eventually, a leader channel extends from one cloud toward the other, testing the path like an electrical scout searching for the route of least resistance. When the connection completes, the result is spectacular. The return stroke lights up the entire channel, creating what witnesses describe as a horizontal lightning bolt suspended in mid-air. These intercloud discharges often appear brighter than intracloud flashes, because more of the channel is visible from the ground, not obscured by cloud material. On summer nights, you can watch massive storm systems lighting up with these intercloud discharges. The sky pulses with light as multiple cells communicate through electrical channels. From the ground, it looks like a silent battle between cloud armies, each flash a weapon's discharge you can see but barely hear. These discharges can be enormous. Some cloud-to-cloud lightning channels extend over 10 miles horizontally, connecting thunderstorms that seem separate from the ground. The energy involved is staggering. A single channel can carry hundreds of thousands of amperes and deliver energy equivalent to several tons of TNT. The current flowing through these channels is immense but brief. Peak currents can exceed 200,000 amperes for a few microseconds. For comparison, a typical household circuit carries 15 to 20 amperes. The power transmitted through a cloud-to-cloud lightning bolt, even for its brief duration, would be enough to power a small city. Research aircraft equipped with special instruments have flown near these discharges to measure their property. The electromagnetic pulses they generate can interfere with radio communications hundreds of miles away. Pilots report their instruments going haywire when flying near active storm systems, even when maintaining safe distances from the visible lightning. What makes this lightning particularly fascinating is that it demonstrates how storms are interconnected. What looks like isolated thunderclouds from the ground are actually part of larger electrical systems, sharing charge and energy across vast distances. The atmosphere is one giant circuit board, and the clouds are components wired together by lightning. But what happens when there's no other cloud to connect to? So the lightning just fires blindly into empty air? Level 2. This is the lightning that goes nowhere. Cloud-to-air lightning occurs when a thundercloud discharges directly into the surrounding atmosphere without connecting to the ground or another cloud. The bolt simply terminates in midair, disappearing into nothing. It's lightning firing blind. Cloud-to-air lightning typically happens when a storm's electric field is strong, but there's no suitable target nearby. The charge accumulates until it must release, so it fires into clear air, the channel dissipating into the atmosphere. These bolts often appear shorter than other types, ending abruptly as if they hit an invisible wall. The science behind this phenomenon involves the breakdown voltage of air. Even without a defined target, if the electric field becomes strong enough, the air itself will ionize and conduct electricity. The lightning essentially creates its own path through empty space, ionizing air molecules as it goes until the electrical potential is exhausted. What's particularly interesting is that these discharges often propagate horizontally from the sides of storm clouds rather than vertically. The anvil of a mature thunderstorm can extend miles away from the main updraft, and cloud-to-air lightning frequently originates from these regions. The charge accumulates in the anvil's upper reaches, far from any ground connection. From the ground, cloud-to-air lightning looks strange and incomplete. You see the bright channel emerge from the cloud base or side, extend outward, then simply stop. No ground strike, no connection to another cloud, just a bolt hanging in empty space for a fraction of a second before vanishing. Storm chasers and photographers sometimes capture these bolts in their images, initially mistaking them for incomplete cloud-to-ground strikes. Only careful analysis reveals the channel never connects to anything, it just terminates in clear air. The visual effect is unsettling, like watching nature's electrical system malfunction. What makes this lightning deceptive is that it often occurs at the edges of storm systems, where the atmosphere around the storm is relatively clear. This is how you get bolts from the blue. Strikes that seem to come from nowhere because they originate from a storm miles away, traveling horizontally through clear air before arcing downward to strike the ground far from the parent cloud. These cloud-to-air channels can extend enormous distances before finally connecting with ground. Documentation exists of lightning traveling over 20 miles horizontally from the parent storm before making ground contact. By that point, the sky directly above the strike point may be completely clear, with no visible storm anywhere nearby. These strikes are incredibly dangerous, precisely because they're unexpected. The sky above you might be clear, the storm seemingly distant, but cloud-to-air lightning can reach out 10 to 15 miles from the thundercloud. People have been killed by lightning while the sun was shining directly overhead, struck by a bolt from a storm they couldn't even see over the horizon. The power of cloud-to-air lightning is identical to any other lightning, carrying potentially millions of volts and tens of thousands of amperes. The difference is targeting. Instead of finding a clear path to ground or another cloud, it's searching, testing the air, looking for any conductive path it can find. But what happens when that searching bolt finally finds the ultimate target? The Earth itself? Level 3. This is the lightning everyone knows. The dramatic fork splitting the sky, the bone-rattling thunderclap, the scorched crater where it strikes. Cloud-to-ground lightning is nature's most iconic display, a multi-million-volt punch delivered from sky to Earth in less than a second. It starts with a stepped leader, a channel of ionized air snaking downward from the cloud, in rapid, invisible steps. Meanwhile, the Earth responds with streamers reaching upward from tall objects. buildings, trees, even people. When leader and streamer connect, a massive return stroke races up from ground to cloud at roughly one-third the speed of light. The air heats to 30,000 Kelvin, 5 times hotter than the surface of the sun, causing it to explode outward. That explosion is thunder. The stepped leader moves in discrete jumps of about 50 meters, pausing briefly between each step as it ionizes the next section of air. This stepping process is invisible to the human eye, occurring in total darkness. Each step takes about a microsecond, and the pauses between steps last about 50 microseconds. The entire leader descent from cloud to near ground takes only 20 to 30 milliseconds. When the leader approaches within about 100 meters of the ground, the electric field becomes intense enough that streamers launch upward. These streamers emerge from anything tall or pointed: trees, buildings, antennas, even blades of grass in an open field. The first streamer to connect with the descending leader wins, completing the circuit and determining exactly where the lightning will strike. The return stroke is where the real violence happens. The moment the circuit completes, electrons rush downward through the ionized channel, while positive charge rushes upward. The return stroke travels at approximately 100,000 kilometers per second, about one-third light speed. The channel temperature spikes to 30,000 Kelvin almost instantly, far hotter than the sun's surface. This extreme heating causes the air to explode outward at supersonic speeds, creating the shock wave we hear as thunder. The process repeats multiple times down the same channel. Additional dart leaders travel down, each triggering another return stroke. That's why lightning appears to flicker. Some bolts deliver a dozen strokes in half a second, pumping billions of joules into a channel barely an inch wide. The electromagnetic pulse from a lightning strike is powerful enough to induce voltages in nearby electrical systems. This is why lightning can fry electronics without directly hitting them. The changing magnetic field induces currents in any conductor within several hundred meters. Even underground cables aren't safe, as the electromagnetic pulse can penetrate soil. The Empire State Building gets struck about 25 times per year. Lake Maracaibo in Venezuela sees thousands of strikes per night, with lightning on nearly 300 nights per year. A strike to a tree can turn moisture into steam so quickly the trunk explodes from the inside out. When lightning hits sand, it melts silica into glass tubes called fulgurites, frozen lightning preserved in the earth. The damage lightning causes depends on what it strikes. Direct strikes to trees vaporize the sap instantly, causing explosive fragmentation. Concrete structures can suffer what's called spalling, where the rapid heating of moisture inside the concrete causes explosive expansion. Metal structures conduct the current relatively safely, unless there are gaps in the structure that force the electricity to arc. About 10% of people struck by lightning die immediately. Roy Sullivan, a park ranger, was struck 7 times and survived each one. The odds of that happening? 1 in 10 septillion. Most survivors suffer permanent nerve damage, memory loss, and chronic pain. The current doesn't just flow through you, it rewrites your nervous system. What makes cloud-to-ground lightning especially dangerous is its unpredictability. Sometimes it strikes with no warning. Bolts from the blue can strike up to 15 miles away from the parent storm, emerging from the anvil cloud's clear sky and traveling horizontally before arcing downward. You can be standing under blue sky, the storm seemingly distant, and still be killed. But what happens when you flip everything we know about lightning on its head, and the bolt shoots upward from the ground instead of down from the sky? Level 4. For most of human history, we thought all lightning came from the sky. But in the 1930s, scientists noticed something strange in photographs of the Empire State Building. Lightning wasn't just striking the building, it was launching from it. Bolts were shooting upward into the clouds above. Welcome to upward lightning, where the Earth fights back. Ground-to-cloud lightning happens when extremely tall structures or elevated terrain trigger their own strikes. When the electric field becomes intense enough during a storm, these structures send up their own leader channel, connecting with the charged cloud base above. The result is a lightning bolt traveling from ground to sky, the reverse of what most people imagine. The physics is essentially the same as cloud-to-ground lightning, just inverted. Instead of a stepped leader descending from the cloud, an upward leader ascends from the structure. This typically requires the structure to be at least 100 meters tall, though mountain peaks can trigger upward lightning at lower elevations due to their exposed position. The process begins when the electric field at the tip of a tall structure exceeds the breakdown threshold of air. This happens when the overhead cloud charge becomes intense enough. An upward streamer launches. Then, if conditions are right, it transitions into a full upward leader that propagates continuously toward the cloud base. The Burj Khalifa triggers upward lightning regularly. Communication towers on mountain peaks see dozens of strikes per year, with repairs costing tens of thousands of dollars. Wind turbines are particularly vulnerable. their rotating blades creating perfect conditions for upward leaders. Some turbines have been struck over 100 times in a single year. Wind turbines present a unique challenge because their blades are constantly moving, changing the geometry of the electric field around them. When a blade reaches its highest point, it becomes the most likely launch point for upward lightning. Engineers have had to develop specialized lightning protection systems just for these structures. What makes ground-to-cloud lightning especially powerful is its duration. While typical cloud-to-ground strikes last milliseconds, upward lightning can be continuous, lasting several hundred milliseconds or even longer. Some strikes persist for over 2 seconds, literally melting communication towers and leaving steel glowing red-hot. The longer duration means more energy transfer. A 2-second upward lightning flash can deliver 10 to 100 times more total energy than a typical cloud-to-ground flash, even though the peak current might be lower. This sustained heating is what causes the catastrophic damage to towers and structures. Research using high-speed cameras has revealed that upward lightning often consists of an initial, continuous current phase followed by multiple downward dart leaders and return strokes, making it a hybrid between pure upward and typical cloud-to-ground lightning. This complexity makes upward lightning particularly difficult to protect against. Mountain climbers report terrifying experiences with ground-to-cloud lightning. Ice axes suddenly start humming and shooting sparks upward. Climbers feel their hair standing on end as their bodies become part of the upward channel. Reinhold Messner described experiencing this on K2, watching lightning streams from his fingers toward the clouds, knowing that any second the connection could complete and send millions of volts through his body. The physics of upward lightning proves that lightning is a negotiation, not a one-way assault from the sky. The cloud and the ground are responding to each other's electrical state, and under the right conditions, the Earth can initiate the strike. Sometimes the Earth speaks first. But what happens when lightning doesn't need the sky at all, and electricity finds a path directly through the ground itself? Level 5. You're standing in an open field during a storm. Lightning strikes a tree 200 feet away. You're safe, right? You're not even close to where it hit. Then, your legs go numb. Your muscles seize. You collapse. The lightning didn't need to hit you directly, it traveled through the ground beneath your feet, and your body just became part of the circuit. Welcome to ground-to-ground lightning, the invisible killer that strikes without ever leaving the Earth. When lightning hits the ground, it doesn't just stop. The millions of volts dump into the soil and spread outward in all directions, searching for the path of least resistance. This creates what's called a ground current or step potential, and it's responsible for more lightning deaths than direct strikes. The current flows through the Earth in a ripple pattern, weakening as it spreads, but still carrying enough voltage to kill hundreds of feet away from the impact point. Here's how it kills you. Your feet are on the ground, maybe 3 feet apart as you stand. When ground current passes beneath you, one foot is closer to the strike point than the other. That creates a voltage difference between your feet. One foot is at a higher voltage than the other. Electricity takes the path through your body from one leg, up through your torso, and down through the other leg. Your heart, nervous system, and muscles are right in the middle of that path. This is why cows and horses die in groups during thunderstorms. Their legs are spread far apart, creating a larger step potential. 4 legs mean more voltage difference. A single strike can kill an entire herd standing in a field. Every animal electrocuted through the ground, without the lightning ever touching them directly. The ground itself determines how far the current travels. Wet soil, metal pipes, underground cables, anything conductive becomes a highway for the current. Lightning that strikes a beach can travel through wet sand for hundreds of meters. Strikes near lakes or rivers send current through the water and shoreline, electrocuting swimmers and fishermen who never saw the bolt coming. Urban environments are even more dangerous. Buried power lines, water mains, gas pipes, sewer systems, all of these create interconnected pathways for ground current. Lightning strikes a street, and the current travels through underground infrastructure, emerging inside buildings through plumbing or electrical systems. People have been shocked while showering, washing dishes, or talking on landline phones during storms, miles away from where the lightning actually struck. The electromagnetic pulse from the strike also induces current in anything metallic underground. This is why golfers are warned to drop their clubs and leave metal carts during storms. The clubs act as antennas, and ground current is drawn to metal objects, fences, railings, bleachers. Anything metal touching the ground becomes a conductor. There's a survival technique called the lightning crouch. You squat down on the balls of your feet together, minimizing contact with the ground and eliminating step potential. It's not perfect, but it reduces the voltage difference across your body. The worst thing you can do? Lie flat. Maximum contact with the ground means maximum exposure to ground current. Ground-to-ground lightning proves that the danger isn't just what falls from the sky. The Earth itself becomes weaponized, and electricity doesn't care about distance or visibility. You can be far from the strike, under clear sky, doing everything right, and the ground beneath you can still kill you. The storm doesn't need to see you. It just needs to touch the same ground you're standing on.